Welcome back to Neural Intel. Today, we're diving into one of the biggest bottlenecks for even the most powerful AIs out there, their memory. You see, every large language model has what we call a context window, which is basically how much information it can see or remember at any given time. So what happens when you need an AI to understand something truly massive? Well, let's take a classic book like Jane Eyre. In AI terms, it's about 240,000 tokens long. And a token is just a piece of a word. It's the language that these models speak. Now, for an AI to actually understand the twists and turns of the plot, it needs to be able to hold that entire book in its memory, all at once. And that's the real question, isn't it? An AI can write a pretty good story, but can it read a long one? Even a state-of-the-art model with a 128,000 token context window, well, it can't even fit this entire book. It has to cut it off, which means it might miss crucial details. You ask it a question about the ending when it's only read the first half, it's going to get it wrong. This whole problem leads us to what researchers are calling the million token wall. Pushing these context windows out to 1 million tokens or more isn't just a little bit hard, it's incredibly, prohibitively expensive. The sheer computational power and memory required just skyrocket, and that really limits what we can do with these models in the real world. Now, people have been trying to solve this for a while. We've tried stretching out the positional encodings so the model can see further, but the accuracy just tanks over long distances. We've tried tweaking the core attention mechanism, but the computational overhead is still massive. And then there are retrieval methods, but they can easily miss subtle but important connections. Basically, none of these are the silver bullet we've been looking for. So when running straight at the wall doesn't work, what do? You get creative. And these researchers came up with something that is, frankly, a bit radical. What if instead of trying to make the AI's memory bigger, you could just make the information itself smaller? And this quote from the paper just nails it. They came up with a framework called Glyph. The idea is simple but brilliant. Stop feeding the AI text. Instead, turn all that text into a picture and feed the AI the image. It's basically visual compression for text. I love this graphic because it shows you the aha moment perfectly. On the left, you've got your standard large language model and LLM, just getting swamped by this long string of text tokens. But on the right, you have a vision language model, a VLM, and it's just calmly processing the whole thing as one compact image. You're not fighting the text problem anymore. You've turned it into a vision problem. So let's define it clearly. Glyph is a framework that takes these huge text files, renders them into images, and then uses a vision language model to read them. And here's the magic trick. A single visual patch from that image can represent a whole bunch of text tokens. So you get this massive compression without actually losing any of the original information. Okay, so the idea is awesome. But how do you actually build something like this? How do you teach a model to read pages of a book like it's a photograph? Well, it's a pretty clever, multi-stage process. Let's break it down. It all happens in 3 main stages. First, they take a VLM and they just show it tons and tons of text that's been turned into images, using all sorts of different fonts and layouts. This is just to teach it the basic skill of reading text this way. Then comes the really cool part. They search for the absolute best way to render the text. And finally, they take that optimized model and fine-tune it to squeeze out every last drop of performance. Now, that second step, the rendering search, is probably the most fascinating part of this whole thing. I mean, think about it. What's the best font? The perfect page size? How many columns should you use? It's this incredible balancing act between squishing the text down as much as possible while still making sure the AI can actually read it. This graph here explains that challenge perfectly. On one axis, you have the compression ratio, how much you're shrinking the text. On the other, you have performance. If you compress it too much, say with a tiny, unreadable font, the performance plummets. But if you don't compress it enough, you lose all the efficiency benefits. The goal is to find that golden star, right in the middle, the sweet spot. So how did they find it? This is what's so cool. They used an LLM-driven genetic search. That's right, they used another AI to automatically experiment with thousands of combinations of page size, font, resolution, you name it, to discover the absolute optimal setup. And what you're seeing here are the winning parameters it found. So, we have a really clever idea and a super smart way to build it. But the question that always matters is, does it work? Let's look at the numbers, because this is where things get really impressive. Okay, first up,
accuracy. Because if you gain all this speed, but the model starts making mistakes, it's useless, right? Well, take a look. This chart puts Glyph up against other top models on a long context benchmark, and the takeaway is crystal clear. Glyph's accuracy is right on par with text-only heavyweights like Qvin 3.8b. You're not sacrificing performance at all. But accuracy is just table stakes. Here's the punchline. It's not just accurate, it is fast. I mean, look at these graphs. They show the speed up for prefill, that's processing the initial input, decoding, and training. The green and blue lines representing Glyph are just soaring way above the baseline. It's not even close. And it all comes down to this one number, up to 4.8 times faster. Now let that sink in. At a sequence length of 128,000 tokens, Glyph's prefill speed is almost 5 times faster than its text-only version. That is a colossal gain in efficiency. Okay, the results are fantastic, but now it's time for our neural signal check, where we cut through the noise and break down why this development really matters at a fundamental, technical level. Because this isn't just another small, incremental improvement. This is a potential paradigm shift in how we even think about solving the long context problem. Let's break it down. First, you're getting 3 to 4x token compression. What this really means is your 128K model can now act like a million token model. It effectively quadruples your context window. Second, that compression directly leads to about a 4x speed up in inference. That means lower costs, lower latency. But here's the most important point. This is an orthogonal approach. It's not trying to fix the attention mechanism. It's going around it. That means you can combine Glyph with any future improvements to attention, stacking the gains on top of each other. So we're left with this final thought. Glyph takes a text problem and solves it by turning it into a vision problem. It's an incredibly creative hack that sidesteps one of the biggest bottlenecks in the field. And it really makes you wonder, what's the next big challenge in AI that we can solve not by throwing more compute at it, but by just looking at the problem sideways? To stay updated on the latest in AI and ML, make sure to visit our webpage, neuralintel.org, and check us out on YouTube. Thanks for tuning in.